Then a reminder of how we are going to solve for x if we have different things. So of course, if we have 3x and we want to figure out what x is, we're going to have to divide by 3, right? If I have 1 over x, in my calculator, I can either do 1 divided by that number, or I can do to the -1. Depending on the calculator, sometimes the button looks like this. Sometimes the button looks like 1 divided by x. Those mean the same thing. And if I have a number equal to the natural log of something, I'm going to do e to that number. So e to the -0.074. That is going to give me what x is. If you're looking for e to the x, it's almost always the same button as natural log, but you have to hit shift first. Okay, so here's our example. And this should be on one of the papers that doesn't have a back to it. I forgot to double side that paper. Okay, a certain first order reaction is 46% complete in 68 minutes at 25 degrees Celsius. What is the rate constant? Often the temperature is not going to be part of our equations. So several of you were throwing the temperature into our colligative property calculations, and we didn't really need that for the pressure thing, right? That wasn't part of the calculation. So be careful about having extraneous information. Okay, we're trying to find the rate constant. So we're going to use one of the integrated rate laws. It says it's a first order reaction, so we're going to use the one with the natural log. And since we're looking for one of these two, I'm going to use the version that has the A and the A0 together. All right, so what are our different variables? Our time is 68 minutes, and it says A has gone down by 46%, okay? But A at time t isn't how much I've lost, it's how much is left, okay? So at time t, I have 54% of A0, okay? So if I have A0 on the bottom, A at time t is going to be 0.54 times A0. Okay, so that's plugging in all of those variables there. Everybody see how I got this here? Okay, this is coming from subtracting that 46 from 100% and then changing it to a decimal. Now, initially, you might think, oh no, I have too many variables. But remember, this is a function. This is like times or plus, so it's not the variable, even though it's letters. What's going to happen to A0? They're going to cancel out. So I'm just going to have natural log of 0.54. So that's the advantage of being able to put that in that fraction form, is that you can see they'll disappear. And so we didn't even have to know what A0 was. Okay. So shift this up. So that's the same thing that was on the bottom. And so now I have -68 minutes times K is equal to -0.6162. And in this case, I don't have a natural log left over. I've already done that. So I got rid of my natural log when I plugged this part into my calculator. So it's just divide. K divided, or divide both sides by the -68. And that should give me my answer. Note both sides are negative, so I'm going to end up with a positive K. All right, for the calculator that you have, plug in natural log of 0.54. Make sure you get that same number, that you're able to use your calculator to get that. Because the biggest problem people have on the calculations on tests is not plugging them into the calculator correctly. All right, let's do another one. Okay. A certain first order reaction has a rate constant. Rate constant. What do I use to represent rate constant? K is the rate constant. So the rate constant, this right here is going to be K. If on a test, I might draw an arrow for myself. Okay, that's K. The initial concentration of A, so that's bracket A with a 0, is going to be 0.69. And I want to know the concentration after 13 minutes. right? So now I'm using my integrated rate law with the A's on separate sides. The reason is because I'm looking for one of those A's. So I want to keep this separate so it's by itself. Because in algebra, we always want to get things by themselves in order to solve for them. All right, so plugging in our variables, initial concentration 0.69, K is 0.0112. Our time is 13 minutes. And so it's going to look something like this. Go ahead and plug this part into your calculator and see if you get this. This is where you can practice closing that parentheses before you do the next part. Make sure you get that same number. Because like I said, the biggest problem people have is plugging things into the calculator correctly. And I'm not going to teach you to use your calculator during the test. Now, when I get to a number, I need to ask myself, is this the answer? Is it reasonable for the answer? So I'm looking for a concentration. Is a negative number reasonable for a concentration? No. This is not the concentration. If I go back to the beginning, this is the natural log of the concentration. So this is where I'm going to have to undo that natural log. Okay, so remember to undo it, I'm going to have to do e to the, and then type in this number. So e to this, and this is equal to negative 0.517. So do e to the negative 0.517. And if you push that E button, it does to the already. You don't have to use the caret symbol on the calculator. And again, on the white ones, you have to do it in reverse. Put the number in and then do shift and then hit the button. Make sure you are getting 0.60. All right, now let's ask ourselves, 0.60 molar, does that seem like a reasonable concentration? Yeah. Now let's compare it to our original concentration. Should it be more than or less than the original? It should be less, and our original was 0.69, and this is 0.60. That's reasonable. So if you get to the end of the problem and it's a negative number, or if it's bigger than the original concentration, you got to go back and look at your math again. All right, so then we have a follow-up to this one. Anybody still need this slide? So same question, but how long will it take the concentration to drop down to 0.21? So we're still starting at the 0.69. We're not talking about how long from our last point, but it's from the beginning down to 0.21. So we only went a little ways. We want to go a whole bunch of ways, okay? So we're going to go back to our equations. We have these two equations that are the integrated rate laws. Since we're looking for time, which would be the better one to use, the top one or the bottom? Which one's closer to having time by itself? The bottom. Okay, so we'll plug it in here. Okay, and then here's our numbers. So try that out, see what you get. So I walked you through the last couple of examples. And again, feel free to talk to the people at your table, make sure you're doing it right. All right, so if A is 1 and B is 2, by show of fingers, which one are you getting? Still need a little more time? Okay, I'm getting some answers here. All right, so a lot of people are saying C, 106 minutes. If our first one was, I forget what the first one was, how many minutes that was. But that was just a short number of minutes, and we only went down by 0.09. We would expect this to be a lot of time. So 1.2 minutes doesn't make a lot of sense. And 31 probably isn't enough to go that far. So this does make a lot of sense. So yeah, 106 minutes is the right answer. Okay. Next one. So this is on the second paper. At 25 degrees Celsius, HI breaks down into H2 and I2 at a rate of K times HI squared. Now, what order are we talking about here? Second order. So now we're not using natural logs. Okay, now we're going to use the equation with 1 over. Okay, so for integrated rate laws, we have to pay attention to what the order is and then pick the correct equation. So the rate constant is 1.6 times 10 to the negative 3. And remember, rate constant is K. So this number is K. And if 0.01 moles of HI is placed in a 1 liter flask, so here they gave us moles and liters. We have to calculate the molarity. Fortunately, 1 liter makes that easy. So 0.01 mole per 1 liter. How long will it take the concentration of HI to reach 0.009 moles per liter? Right. So here's our numbers. I'm going to use this equation. Now you can do 1 divided by for each of these. So we can do 1 divided by 0.009, but put it in parentheses if you're going to do that. Or you can do 0.009 to the negative 1. That works as well. A lot easier to write without fractions on my PowerPoint. So I have it as to the negative 1, but that means the same thing as the reciprocal. We have all these numbers and then T's over here by itself. So it's just remembering how to rearrange. Remember, I can't divide this until I get this part by itself. So that's another mistake people often make. I want to have whatever my variable is attached to. The variable and that number has to be the only thing on that side before I can divide that off. So first, I'm going to subtract those two things. So that essentially amounts to 111 minus 100 equal to this times. And that 111 is what I would get if I put 0.009 to the negative 1 in my calculator. Or if I did 1 divided by 0.009, I would get 111. That's where that comes from. Okay, so I can do that math in my head. That's 11. So I'm going to have 11 divided by the 1.6 times 10 to the minus 3. And I'm going to get 6,900 seconds. Everybody know how long that is? Yeah, me neither. So we're going to divide this by 60 to figure out how many minutes this is. Because there's 60 seconds in a minute. So if I divide by 60, then I get, it comes out to about 115 minutes, but we have to round to 2 sig figs because we only have 2 sig figs here. So we have 120 minutes. Okay. So we'll do a few more examples on Friday. I would definitely take a look at that section 11.4 now that we've gone through it in class, read it in a little bit more detail, try the example problems that are in this section. Make sure you can do those because they will have the explanations. They even have follow-up questions to the examples, so you can try those out, see if you get the correct answers. So definitely do that before Friday so you can start to get the hang of this. Any questions? All right, see you all on Friday.